What I wanted to do today was to try to give you a sense of what I think is part of the landscape of reasoning about software-defined networking. So instead of giving you one particular topic in extreme depth, so I'd submitted an abstract to talk about tierless programming, what I thought would be interesting instead is to try to give you my feel about what I think are the many different dimensions with certain sort of point solutions, but also as a way of provoking some discussion. And there's plenty of time in this talk for discussion, so jump in anytime. Yeah, and I won't follow you to the restroom. So. Good. Okay, so let's start by reminding ourselves, especially I know we have a few PL people here who maybe are not that familiar with what we're talking about in software-defined networking. So just to set the stage a bit, traditional network, you've got a bunch of boxes that do specific functionality. They're locally configured in some complex configuration language. Any of those of us here who've wrestled with iOS specifications in the past recognize how painful this used to be. And now apparently everything is awesome. And everything is awesome because we now have a single controller, a logically centralized controller. So the switches are now typically dumb, and the controller is running arbitrary software. And all that the switches really do is that they remember instructions that are sent from the controller and store them on the switch for later re-execution. Okay, so flows get initiated, the controller makes a decision, the controller sends out signals to these switches, the switches remember the signals, and at that point the network basically works as fast as it used to before, and so now we have the ability to have some piece of software telling us what the network does. Okay, so that's called software-defined networking. And I remember when one of the early talks or papers I saw used this phrase, the power of software in your network. And of course, from networking perspective, this was an awesome thing. Right? Maybe being a little more of a cynical persuasion, I was like, oh, great. Now we can have all of the same problems we have in software in your network as well. Okay? So,
To be fair, those were there already.
Now we have new ones. Okay? So, so here's the sort of typical stack that we have. We have some data plane that runs maybe some simple match action open flow rules, though of course, there's people here who know far better than me all the ways in which these protocols keep changing, and there's much more stuff that's now happening in the data plane, even in open flow. There's a control plane, and the idea here, the selling pitch here, is that your control plane could be running, Java or C++ or whatever you want, some random program in some random programming language. And in fact, the reality is there's actually one more thing here, which is this, state, right? I mean, networks are stateful things, and so there is state behind the scenes. And the state could be managed, as I said, this is logically centralized, but in fact often distributed. And so you also have to deal with distributed state in the back. Okay? Now, this is a picture that we've seen before, this idea of having multiple tiers of forwarding rules, control logic in a data store. And it's actually not very different from the same three-tiered architecture we've seen before for the web. Right? So you have some kind of database tier there that's storing persistent state. There's a thing that's making decisions, that's sort of your server or your business logic. And finally, there's a client tier. Now, of course, these tiers are really different, right? I mean, this one is a much lower level tier. And in particular, there's a critical difference between these two tiers, which is in this particular case, in the networking case, there's no presentation going on. Okay? I view this as a wonderful thing. There is no JavaScript yet running on our switches. Okay, let's try to keep it that way. There's no CSS and everything else to worry about on the switches. Okay, but otherwise the analogy holds up pretty well. Okay, so what could go wrong? Well, remember the idea is that the controller decides what the behavior of the network is, and the switches in some sense should be thought of as remembering those decisions to improve the performance of the network. Now that's a maybe very PL-centric view of the world. I would gladly invite disagreement with that point of view. But let's just take that as a perspective, and then we can talk about what things go wrong, in part because we have multiple tiers. Well, if you think of this tier as definitive, this is the thing that tells us what truth is, then this is just sort of a reflection of the truth. Then you could have inconsistent packet handling. You might have a switch that fails to notify the controller. And that's actually a problem when the state needs to be updated and now the controller never finds out and therefore the state never gets updated. Sometimes it might be that the behavior is fine, but you end up with many more notifications than necessary, and so you end up with a performance hit. Of course, now you've got code, right? I mean, I've written papers and built tools on program analysis of iOS. That was no picnic, but let me tell you, for analyzing C++ is no better. Okay, so at least there we had essentially a domain-specific language, and we could find things in the language more easily. Now we have code that can basically do anything. Okay, and this one is a little subtle. Okay, if you think about what's happening over here, let's go back to the web analogy for a moment because I think it's especially useful in this setting. On the web, what your server is doing is it's generating code that runs on the client. Right? At least figuratively, your server program consists of a great big string there that says, here is the JavaScript I want to send down to the client, right? And often it's a dynamically generated JavaScript string. You might have a pretty API for it, but that's in essence what it is. It's generating a string, okay? Well, that's what's happening here too, right? If you look at the code that's running on many controller apps, it's generating open flow rules. It is generating a program in another programming language. So to truly understand the behavior of this stack, we have to be able to analyze this program relative to the code that it's generating to be able to ask questions such as, is there inconsistency in the packet handling? Is it sending too many packets? To answer those questions, we have to be able to deal with program generating code. And our state-of-the-art of verification technology is pretty nice, but it's really not that great to begin with, and it certainly doesn't handle program generating code in random third-party languages, okay, in DSLs. So, there are many other things we would like to know as well. So what I just gave you, or you can think of as low-level correctness issues. Like this is the stupid stuff, right? This is what programming languages do for you, is they get rid of stupid things, right? It's like safety layer of the network. And then you can talk about application-specific properties, because the previous things that I mentioned, you really don't want any program to exhibit these problems. But then for a given application you're trying to write, you can ask a whole bunch of questions. And I'm going to return to these questions so you don't have to read them very carefully. But things like, if you're doing a NAT, will it be performed on all packets? If you have a firewall, could the blacklist be penetrated, and so on? Okay? So this is what we normally think of as verification, but we'd like to be able to do it in the context where we don't have the low-level problems to begin with. Make sense? Good. So I haven't heard a question yet. That means you either agree or you're reading email. Okay, you're reading email. Okay, good. Okay, so let me talk very quickly about static verification of SDN programs. So now I'm going to go into the part where I'm trying to give you a landscape of reasoning issues. Okay, so I'm going to start by talking about verification, and I'll tell you in a few minutes what I mean by verification as opposed to other things. I'll hold that in suspense. And by static, I mean before we run the program, right? The equivalent of a type checker. We do it before we ever run the program. Okay, so starting with this set of properties. Now, here's where I get to play a trick, right? This is netPL. So in netPL, I'm allowed to mess with the rules a little bit. In particular, I'm allowed to perform magic and make all these problems disappear in one fell swoop. Okay? I will define away the problems by inventing a programming language. Now this will piss the hell out of Colin Gordon, okay? And he'll argue heavily this afternoon about why this is terrible and how he can't get anything to compose and blah, blah, blah. But the fact is this is netPL. You've got in this room, which means you've accepted that this is an okay way to solve things, okay? So the language we built is a language called Flowlog. And the critical thing about Flowlog is we merge all these tiers together, okay? What we actually do is we program as if we are on the central tier, right? That's the logic. That's the interesting part, okay? We auto-generate, and so it's a relational language, so the database part is actually very easy to map to. The low-level tier is taken care of by a compiler, right? So one version of this talk, I would have talked about all these in great detail. I would have spent 45 minutes telling you about the compiler and so on. I'm not going to do that this talk because, as I said, I want to draw you a much bigger landscape. But what Flowlog does is has a compiler that will generate the rules for you automatically. And there's some nice properties that the compiler has. In particular, it has some optimality properties. So it will not generate a message from a switch up to the controller unless necessary. And it only generates sort of the necessary things, etc. Okay, so some nice properties that we get by virtue of building a programming language for this purpose. Okay? And there's some other details about Flowlog, like it's the right way to think about it is it's similar in spirit to something like SQL, where the language is limited in power, but it has the ability to call out to third-party libraries because we're not going to rewrite all the existing Java and Python and all these other libraries that all do useful things. So we'll let you call out to them by providing like an external API, which is roughly, think of it as stored procedures in SQL, right? That's the right way to think about that part of the design. Okay, so because I have this language and this compiler, the first set of properties automatically goes away. What I want to do is give you a little flavor for programming in Flowlog, just one slide. Okay, so let's write half of a NAT. Okay, so we're going to write a NAT. What is a NAT? Well, a NAT has state. It has a table that tells us what addresses we're mapping to what ephemeral ports. Okay, so we're going to have a database table. We have to keep some kind of state around that tells us what the next available port is, the next unassigned port. And now two things can happen. Either we're in an existing flow or we're in a new flow. Okay? So in an existing flow, when a packet arrives at an internal port and the NAT table knows how to translate it, basically that's the definition of an existing flow, right? You look it up in the table, it's there, that means I've already seen this before. Well, we just rewrite the headers and forward the packet. Okay? Otherwise, it's a new flow. So when a packet arrives to the internal table and the NAT table doesn't already know how to translate it, well, increment the new port, allocate a port in the NAT being that table, forward the packet to the headers rewritten. Okay. Now I'm giving you English. The actual code looks it's a Prolog-ish data log. It's a data log syntax, and it's sort of the bastard. The syntax is kind of the bastard spawn of data log and SQL. Okay, but I've written it in English, but it's about as many lines of code. Yeah.
I guess I'm a slide too late, but I'm not sure I believe all the problems go away.
Ah, okay.
I mean, you said you want to verify all these various properties that you listed, and they all sound very convincing.
Okay.
But how do you know? I mean, now you've made a language. You push those problems to someone else, right?
So we push the problem to the compilers. Yeah.
Do you know? I mean, do you have a proof that the compiler?
We have a hand proof of the compiler's correctness. That's right.
Ah.
Yeah.
Okay.
Yeah.
Nice.
I'm a PL person.
So they don't magically go away, right?
No.
You did a lot of stuff.
Yeah, but from the developer's point of view, it's magic, right?
Okay.
It's gone. Yeah. Yeah. I mean, Java gives you soundness as well, and we don't think of that as, it's a lot of work for somebody at Sun or something, but
it doesn't give you these kind of properties, at least not for free.
No, so the point is, powerful compilers require a lot of work, but powerful compilers give you serious guarantees. That's it. Okay?
Isn't SQL a better analogy than Java?
Oh, yeah, so that's right. SQL would be a much better analogy than Java.
Have you used SQL?
Sure.
Do you believe that it actually works?
Give or take. Yeah.
Good.
Same thing.
Believe it just as much, okay? So, as I said, this is a slightly sketchy version of the program, but it's maybe about 3 or 4 more lines of code. And the key thing is that's it, okay? Notice that what's not on this slide is any statement about individual switches. There's no statement about code generation. There is no code generating code on the slide, right? This is the specification essentially, and the compiler is going to generate the code for you. Yes, go.
So, I've done a lot of work with data log languages, and I've done presentations where I can show a couple rules, and this sounds so easy to reason about. We just have these tables that we kind of reason how lines flow through.
Okay.
But when you start to write more expressive programs, like we tried to code up, Paxos and Datalog, then it becomes a nightmare to understand. And I'd much rather, even though you save orders of magnitude in terms of lines of code, I'd rather write it in C than do you have any
Go ahead.
do you have any sense? What's the I guess the
we're
largest
writing
example?
applications in Flowlog. Okay, I think of this as an experiment. Right? So I'm definitely not a good standard bearer to stand here and say it's in Datalog, therefore everything is automatically better. Right? So our choice is simply a language that's limited to make it possible to do the proofs about the compiler, okay, and to something that we know how to implement. Right? That's all we really care about, and then verification because the language has limited expressive power. Is the Datalog way of writing things the right way? I'm not dogmatic enough to say it is. Okay, I'm not even completely convinced it is. What I don't know is what is a meaningful, say more imperative surface syntax to impose on the language. This is an imperative thing too, right? So I don't know, and I think sometimes these language disputes are, I'm going to think of it as, so there's a different project we have where we think of Flowlog as simply the target of a compiler. So we take iOS specifications, we compile iOS specifications to equivalent programs on an SDN. Okay, so this is a migration path. It's a project called Exodus, right? Haha. So it's about giving you a migration path from existing systems to SDNs, and there it's just a target for a compiler. You could be targeting anything, and it happens to target this because it gives you an efficient compiler. Okay, I'm not going to be the one to stand here and tell you how data log is the way of the future. Okay. Yes.
Who's the intended programmer in Flowlog? So is it for application programmers or network operators? What's the
It's really for application programmers. Yeah. And application programmers, especially who want to be able to maybe write several different programs and compose them together through shared state, I think it's really good for that. For NetOps, maybe not so much. In fact, I'm going to talk a little bit about NetOps in the second part of the talk. Okay? And I'm going to give you a different language actually for NetOps. How's that? Okay? All right. So, let's talk a little bit. I want to just tell you for a moment about verification questions. So as I said, we might have properties like this we want to prove, so maybe a statement about your ARP implementation. One thing to observe is when we go back to this three-tiered picture, our properties actually talk about many tiers at once. Okay? Here's another, I have a few more, but it doesn't matter. So here's an example where really it's saying something about the caching, it's saying something about the request, and it's saying something about the controller handling the reply. And if you have a tierless language, the coloring is me shading it in, right? This is not, I don't write the properties in multiple colors. I just write my property about this tierless program. The verifier can ignore the existence of something of the compiler. The verifier verifies a property about the program, and I get to make statements about multiple tiers. If I had a program that was generating open flow rules explicitly, I would need to write verification statements about the generated code as opposed to the generating code. People who've done verification know how complicated that is. People who haven't, you'll just have to take it on faith that this is not an enjoyable thing to do. Also because many verifiers simply would have no idea because, it's some string or some library, and how do you even talk about that meaningfully, okay? So that's another benefit you're getting out of the tierless approach, not necessarily the surface syntax, okay? All right. So I just want to tell you in one slide what we do. So, basically this is what it looks like. It's data log. You compile data log to first order logic. And it's actually a subset of data log for which we have some nice decidability properties. And you turn the crank, first order logic solving now is a pretty well-known thing. I'm not going to go into that more. Okay? So that's the very first thing I wanted to say about reasoning about networks. So I gave you this set of examples, and I said I'm going to talk about these in more detail as we go along. So something like will NAT be performed on all packets is simply just a statement about the controller program's behavior. Okay? Now, when I get to a property like can a blacklisted host penetrate the firewall, I'm no longer just talking about the controller. Somehow, I need to also know something about the shape of the network, right? Like typically I have one firewall for the network, but I have to know something about the topology to know that there's no way to breach the network by going through something that's not the firewall in the first place, right? So now we get into things that Flowlog on its own cannot handle completely, right? All it can say is, well, the firewall works properly, but I don't know anything about what your network actually does, okay? So these other things are even a little more complicated. Like, can my network ever route packets in a loop? Is really very strong statements about not only the routing software, but also of the full topology. The firewall thing is usually straightforward because you have firewalls at well-defined like ingress points or something like that, and it's not so bad. But things like routing in the loop really require you to know a lot about the topology of the network. And then when I get to questions like does traffic traverse the network in say 15 milliseconds, I can't hope to do that statically, right? My program is of only limited value in telling me anything about what the network does. So now I want to start telling you about the landscape, right? So I started by telling you about static properties, and in Flowlog we've done two different things. We've used model checking for topology dependent things and used this first order logic solver for topology free things, okay? So you can do some reasoning with topology, a lot of reasoning without topology. But now I want to go beyond this kind of static verification that sort of the PL community normally does and tell you about a few other things. So, first of all, how many of you have operated networks here? Good. All right, okay, at least 2 people. Here's what I like to do. Just go check in your back pocket to see whether you've got a list of properties sitting around that you're itching to get verified. Probably not. Okay? So this whole premise of verification, traditional property verification, is predicated on the idea, so these are all some fancy symbols, but what they basically mean is, does this program satisfy this property? If you don't have properties, the verifier does nothing. Okay? Sorry?
Looks like empty set.
Yeah, your empty set of properties. Well, in some sense, your program satisfies the empty set of properties. Like, sure, yeah, it's fine. Okay? So the thing to note is, verification is often not our real goal. Our real goal, our ultimate goal, is to have confidence in our programs. Just like you asked me, how can you be confident about your compiler? Okay? Our goal is to have confidence in our programs, and there's many ways to acquire confidence. In particular, one important modality that developers and maintainers of networks really care about is, I have a network that works, right? Now, works obviously is in quotes. If you're like a hardcore verification person, you'll put like all sorts of quotes around it. But what it means is, maybe you did some verification, but you also did some testing, and you've monitored it, and you're running it, and you've observed that the thing seems to be working fine, okay? And now you have to make a change to your network. And the change is either, there's a configuration change, or you need to add some functionality, or you did find a bug and you need to fix the bug. And the question is, how can you transfer the confidence you had in the previous network to the new network? Okay? That's the real question we often want to answer. So we have this thing, this nice setup, which is great if we have properties, but if we don't, we can still do things, for example, with different copies of a program. Okay? So this is something we call differential analysis, where what you do is not compare a program and a property, you compare 2 programs. Okay? This is a phrase I got from sysadmin at a very major US corporation, so he didn't let me name which corporation. These changes are made by staring really hard, then crossing our fingers and praying as we upload the changes into the production network. And in fact, I have now been to several sysadmin conferences, and the most common word I hear is pray. This is the current differential analysis technique that people have. Okay? So that's nice, works well for some people, maybe we can do better. Right? So now I'm going to talk about static property-free analysis. I don't have properties, all I have is multiple versions of a program. Okay? So I've given you here 2 versions of this NAT program. What I've done is I've changed things very slightly. So this is not an interesting change, though this is a bug we actually had in one of our versions along the way. So the difference is, in this case, the NAT table just has an entry for the source IP. Here it has for the source IP and port that it's coming from. Okay? That's basically the difference. Am I only remembering the IP address, or am I remembering the IP and address and the port of the message that's trying to be sent? Okay, so what I can do with a differential analyzer is I can ask questions along the following lines. I can ask about the behavioral difference in terms of packets, and I can ask for the behavioral difference in terms of program state. So I can ask, will NAT 1.0 send an output packet that NAT 2.0 does not? Or I can ask questions like, will NAT 1.0 and 2.0 change states differently? Okay? Those are the basically 2 ways you can observe differences, either in the packets or in the state. Okay? All right. So what you would get as output from our tool is, again, it turns into first order logic, goes to a solver, etc. But it comes back with concrete scenarios. Okay? It'll give you a scenario along the lines of, consider a packet with the following shape. Here is the way that packet will differ in the 2 different systems. So for example, in the example I just showed you, what I'm really asking the system is, find me a pre-state, an incoming packet, and a departing packet such that they will be different across the 2 systems. Okay? As you can guess from the way I've phrased this is a search problem. Okay? And search problems are what solvers are pretty good at these days, so we turn it into a reasonable solver problem. Okay? So in this particular case, it would give you the answer. It would say, look, let's assume, I'm going to construct an artificial state for you, and let's say I've already mapped that address 10112 with port 10001. I get a new packet now from 10112 port 5000 instead. Okay? Well, version 1.0, which didn't care about the ports, from port 54000, and I've mapped it to the new ephemeral port 10001, is going to map it. The second one's going to say, I've already seen this before, I don't need to do the mapping. Okay, that's the fundamental difference. So it's a concrete example. It's telling you in one case it would actually do the mapping, in the other case it would not do the mapping, right? And similarly, if I ask for a state change, it would say in one case the state stays the same, in the other case it's going to add another tuple to the relation. Okay? And the key thing is this is an automated process as long as you can think to ask a question along these lines. So if you simply ask what are all the situations in which the program does something different, right? You will start getting output. You can then think of that output, which sometimes can be quite considerable, right? Because even small changes can have big deltas in behavior. You can then ask further queries, you can do filtering, you can narrow those queries and so on. But the key thing is you don't have to come up with clever properties. This is an important, I think, HCI question here. It's a modality issue, which is, will the system sit passively if I can't come up with something interesting? Or can I just give it something I already have and it comes back and says, here's a bunch of things you may or may not have known. And from that, you can start to get more questions, right? You can look at that and say, oh, well, show me all of the ports that are involved. Show me all the IP addresses that are involved. Show me all the new ports that are involved. And you can start to filter your query because it's provoking you with some initial ideas. Verification does not provoke you with initial ideas until you have properties. That's the key difference. Yeah?
How powerful does a theory need to be? So the solver is the solver for what theory?
These problems in our case turn into a restricted subset of first order logic. It's called the Bernet-Schoenfinkel class. And so we use we have a stronger version of the Bernet-Schoenfinkel theorem that gives us, it's a typed version of the Bernet-Schoenfinkel theorem. So that's basically what we're using. And so that lets us give complete answers, so we can generate bounds and get complete answers on that subset.
So the complexity class there is quite large, though.
Yes,
so
yes.
How does it scale?
Yeah, so scaling is a good question. What I can tell you is for the experiments we have done, so we've got about 15, 20 different network protocols and some applications, like actual running applications, for which we can answer questions in about a second or less. Okay?
For the logically uninitiated, how complex is the decision procedure for Bernet-Schoenfinkel?
How?
2 to the something?
Some probably, yeah.
Like omega.
Yeah, exactly.
For,
Exactly. Yeah.
Did you run into applications for which it was not feasible to...
Very honestly, we have not, and that's probably because we're not. We have not. Maybe we just haven't written them. So I'm not at all claiming that they don't exist. I'm just saying we haven't run those. Yeah. Okay. All right. So here's an interesting thing that occurs. I told you that I asked Anil to check whether he had any properties sitting around, and he didn't. But there are actually properties that maintainers and admins often run into that are properties about changes. When you make a change to your system, there is usually some implicit property you had in mind. When I change this, I want to make sure that only the following things were affected. Or when I made this change, the following thing is not affected. Right? I made a change to the contractor's access to the network. I want to make sure that all internal employees are not affected, right? So these kinds of partial properties we often have in our heads when we make changes. They are not properties about the system. They're properties about the delta to the system, okay? So we call these differential properties, and we can state and verify differential properties as well using the same stuff that I've talked about. So, for example, if you had, here's an example in this particular instance. If 2 incoming packets are given different ephemeral ports in NAT 1.0, they're given different ephemeral ports in NAT 2.0, right? They're still, that basically the change I made to the program doesn't change that. So essentially what it's asking is, look, I've got source IPs here and I've got source ports over there. With NAT 1.0, maybe 2 different packets got mapped to different bins, right? 2 different ephemeral ports. Now when I go to 2.0, will it still be the case, right? That I'm still going to preserve that mapping? And the answer is, go find a pre-state and, a set of packets, and the answer in this case is yes, that's not a problem. You haven't broken that property, okay? So and this is something we've been doing now for several years in a few different contexts of verification, where even though you don't often have very good properties about systems, you do have very good properties about changes, essentially frame conditions, if you've heard that phrase before, right? Frame conditions are, and nothing else changed. And nothing else changed are really useful properties, and that's what maintainers often want when they're maintaining a network, okay? So for verification people out there, think about how you might turn frame conditions and more slightly richer things than frame conditions into a verification methodology over pairs of programs. Okay? So there's lots of things you can do. You can check configurations, check for upgrades, etc., etc. Basically, what this change impact thing, this differential analysis thing lets you do is to ask what if questions. If I change my program this way, what will happen? If I want this change, what do I need to do? That kind of question. Matthias, and then Anil.
So my name is Shriram.
Okay.
The dual question really is, how big is the change that you can cope with? I mean, you said differential properties, but I might start with an empty program.
That's right.
Swap in a big one.
That's right.
What do you do?
That's right. So even small changes to your programs have surprisingly large deltas. Okay, this is absolutely the case. We have often been surprised when we make a small change, and in fact, one of the things we use it for is to confirm that a small input has a small output, right? And it's sometimes subtly not the case. So, what do? You first you confirm that the set of outputs is as small as you wanted it to be. But this is why we think it's important to not simply produce all the outputs, but to actually give you the ability to interactively go back and ask questions about the outputs. So we treat the set of outputs, the set of deltas, the delta, as an object that you can then further query. Right? You can ask questions about that object. You can say, show me show me these kinds of things, show me those kinds of things. Think of it as a great big database, and now you want to do database things to that object. That's the right way to think about it.
So what I'm asking is it possible that somebody does not know how to ask the right question about this database?
It's always possible.
Right, and
Yes.
that's clearly possible.
Yes. Yeah.
And so do you have any experience of when people, and you have incredibly experienced people, presumably querying your databases, but if you threw this as a normal operator, would that operator, without a PhD training, right, be able to ask the right questions about this database?
Yeah, that's a good HCI question, and it's something I'd like to think about more. In fact, we're doing something slightly different, but I think is also relevant to this, which is so when we produce these outputs, right, we produce models, right? We produce first order models. So it's scenarios. It's nice and easy to understand. It's like this goes to this, that goes to that. It's a nice concrete mapping. What they really are is first order scenarios. Here's a very simple question that I believe nobody knows the answer to. One of the things we do is we have a minimization procedure that gives you the smallest possible model. Okay, takes a big model, shrinks it down. Are small models good or bad? I mean, on the one hand, like how could you object to a small model? It's obviously better, right?
It's the holy grail in testing.
It's the holy grail. On the other hand, there's actually two different use cases here. One is I'm verifying and I'm getting a counterexample. The other is I'm just trying to explore and understand my system, right? Like change impact, I just want to understand the set of things that can happen. We've started to do actual user experiments now where we're finding that for verification, it appears that small models may be better as counterexamples. That's perhaps not so surprising. For exploration, small models may actually be quite bad. Okay?
Exploration?
I'm just, generate me models of this thing, right? I don't have a property I'm trying to falsify. I'm just trying to understand the system, right? Like
humans want to be able to take their intuition down to elements of the model, and small models tend to conflate lots of different parts of the
not necessarily. Small models simply get rid of unnecessary facts. So if I have fact A's, if I have a set of facts and I have a new fact and it's a consequence of the existing facts, then I don't need that fact because it's just a consequence. So that's what small means in this case.
I think people need redundancy when they explore, but they don't want redundancy when they test.
There are many possible hypotheses. So one of the interesting questions is how do you formulate this as a mechanical Turk activity? Okay? Because you can't go to Mechanical Turk and say, here is an alloy specification, which output would you like? So I think the most interesting thing we've done is figure out how to turn this into a Mechanical Turk activity. Okay? But we're finding some interesting things. The other thing is most model finders, Z3, alloy, whatever, give you one model output at a time. Why one? Right? So what we're now exploring is being able to give you a bigger than what I call the fat middle, right? So you want models that are not too big, not too small. You want to give them a reasonable size model, but maybe inside the reasonable size model, inscribe the minimal model so people can see, oh, that's the core of it and that's the bigger version of it. So you can, you can study the interplay. So there's some very interesting HCI questions here, even at the simple level of what model do I present before we even get to this, but we're starting to investigate those questions. Yeah?
Just a remark and question. So
Please.
I think you can ask C3 to generate in principle all the models for a particular problem, but that doesn't help you too much either, I guess, in this case.
That's right. So when I say all the models, what I mean is it does generate all the models, but it only generates them one at a time. The thing is, what I want to do is when a user is looking at them, right, their attention has to switch from one model to the next. And that's what I'm asking. Why don't we try to overlay these and try to present more of the space of models while still presenting concrete models as opposed to just, the set of formulas is all of the models, right? But that's not an interesting...
It tries, technically behind the scenes, it tries to generate them more efficiently than just individual queries, but I guess what it gives you is...
That's right.
Which probably doesn't help you much.
That's right. So what we're hoping is to do the HCI research and drive it back into how the model finders generate and present. Yeah.
Cool.
Yeah.
I had a question too. So
Please.
Have you seen scenarios in which you present these models to expert users and they say these are not the useful scenarios? I mean, have you tried that on users? Could it even be that the small models are like extreme cases that they know for reasons that are not explicit in the program will never even happen?
No, that's even with non-expert users, we're starting to find that.
Okay.
Yeah. So this is, we've spent about 2 months working on this now, and it seems to me a wide open question because there's a lot of cognitive science involved as well that I don't really fully understand. Yeah. But I think it's interesting to ask this question and try to get some answers, yeah. Okay, so what I've now told you about is the static world, right? Property-based, property-free, and already in the static world there's a topology-based, topology-dependent, and topology-free difference, okay? Now I want to go back to thinking about properties again, and I want to talk about properties like this one, right? So these are properties we can only talk about dynamically. So it's something we want to have be true about the system, we can only check it dynamically. So, yeah.
On the other hand, however, since on the network kind of availability of hosts might fluctuate with congestion, isn't, for example, a blacklisted host penetrating firewall? I'm trying to think
so,
of their reachability is on the network is a static.
Right? So in fact, that's exactly what I want to get to, is to say that, all these, on a network, all these things are a little blurry. The static dynamic is really kind of blurry, okay? So that's why I want to talk about the dynamic case now, okay? Because we can't skip it, right? Much as the PL community might wish it can't skip it, that's all, okay? All right, so there's several contexts, right? We've run into this, of course, in testing and debugging flow log, right? Because we have to get it right, and it's not easy. Understanding third-party libraries, you try to bring something like route flow. As we said, we have this call-out mechanism, and I need to know what it's doing. Of course, there's this great paper. I assume many people have seen this paper, right? Basically, it says like switches are, crappy hardware, right? We're still getting there in terms of SDN quality. So, there's lots of reasons why what you want to be able to do is property given. You have a property and you want to verify it, check it dynamically, okay? And of course that's going to be topology inclusive because you're there dynamically. You can see the network, right? So you have the topology accessible. Okay, so here's a question. How do you test a stateful firewall application? I've got a firewall. I claim it's got state obviously by virtue of being firewall. How do I test it? Well, obviously you send a ping, you get an ACK, check whether you get it. That doesn't actually tell you the whole truth because it might actually be broadcasting things. It might be flooding the network. You don't know. Just because you got an ACK doesn't mean that other people didn't get pings as well. Okay? All right. Well, next thing we can do, data plane verification, right? So you take your flow logs, you send it off to Veriflow, which by the way, I'm not mocking, is a wonderful tool. But, so that's great. So let's say you send a ping and there's a packet in and this thing maybe sends both a packet out and a flow mod. So the flow mod is going to be captured in the flow table. The packet out is not captured in the flow table. Okay? So that's not quite going to do it either. You can send probe packets and check for every single thing that comes back from the controller. Does it send a flow mod? Does it send a packet out? Be very explicit. Of course, now if you make small changes, all of your test cases break. Okay? So what we really instead want to be doing is we want to be able to write a description of the intended behavior. Right? Write something closer to an actual property statements. When network events come in, run them against the property statement and get alerts when the properties fail. Okay? So for example, in a firewall, we might have properties like this. So a packet arriving on an internal interface is passed through. Packets arriving on an external interface that are in an existing flow are passed through, and all other packets are dropped. Okay, so a conjunction of these three properties. That's what I really want. That's a basic description of what the correctness of a firewall is. So we've been working on this thing that we call scriptable interactive monitoring. The idea is you get a stream of network events, and you can either write a script on it, or you can do it with a REPL prompt. And the things we capture are data plane events. We pull out data plane events, we get control plane events, and we also check for northbound API messages, because that's really the right combination of things you want to be able to monitor. Okay? And you get these packet in, the packet outs are expected to go within some amount of time. All the violated expectations produce a stream of alarms. So let me show you some actual code. Okay? So here's the thing we're trying to check for. Packets arriving on an internal interface are passed through to the outside. Okay? So I'll show you the code. Don't worry, you're not expected to be able to read the gray. Okay? So I have a stream of events, and I'm going to filter it by all the events arriving on the internal interface. Okay, so if they're arriving on the internal interface, all those that filter that are in this arriving stream. So then I'm going to filter that furthermore by the things that arrive at the internal port, right? And I'm going to filter those by what are going out in the departing stream. And so essentially, I have some set of expectations for packets of the arriving stream. Some of them go through, some of them don't go through. The ones that don't go through are my error stream. Okay? And so my errors are, I take each packet and I expect it to arrive at the departing interface. It has to be the same as the internal packet, and it has to happen, say, within 100 milliseconds. And a flat map is something that basically combines all of these streams together. Okay? So this is working code. Again, this is the entire code that we use for monitoring that particular property. It's written in reactive Scala, and currently it works on top of, so getting this to work on an actual network with actual packets is an interesting challenge. We're looking at how we can make that happen. Right now we're doing with the simulation environment. Yeah?
So what if I wanted to make that 100 milliseconds dependent on the previous distribution of errors or something, some quite rich semantic? So is that intended in the language that you can do dependencies on all previous results?
That's right, that's right. So that would be like an integration across the past history of the stream.
Right.
So this is really FRP.
Yeah, that's
Yeah.
right.
So you would integrate across the past history of the stream, and yeah, okay. So this is a very different language than the language I showed you earlier, and I think in this case, sort of a functional reactive style is exactly the right way to think about it. You get event streams, and you want to be able to apply, map, filter, flatten these event streams, and produce a set of alerts as an event stream as well. Okay. Yeah.
Do the events or the properties that you're interested in, do they refer to events on the same packet, or is it more like on a full history of the...
You have the choice in what property you write. It's just how much space you will end up consuming because of how much history you try to track, right? So the thing that I showed you has minimal history, and that's one of the things we're trying to do, is because we want to eventually be able to take this program and compile it down to the switches, right? So anything that is history-free, we can compile to run completely on the switch. Anything that's history-driven, it's a question of, open flow counters, it's all the usual sort of implementation details. So, sorry?
I'm wondering how you did this program fast enough as a reactive program to fit in these intervals. Feature work, I understand.
Well, I mean,
the space you consume if you go for historical stuff.
Yeah, but these are not. I mean, many of these things are very, very likely history. I mean, networks don't do a lot of history for a good reason. Yeah. They're networks, right? They wouldn't run in the first place. Yeah.
What if you want to lift up all of this into HTTP, for example? So you have to do a little bit more flow track, a little bit more parsing.
Yeah.
At this point, do you have a sense of what needs to change throughout the entire system? So we move from NAT to something that's a bit more stream protocol parsing based. What's the most painful part of that if you had to add it to the entire system?
So, in fact, I would claim that working at something like the NAT level is the most painful, because that's where you're at the lowest level and you don't have a platform to run on. Mm-hmm. Once you're willing to move up the platform, I mean, the thing I've always said about HTTP is the great thing about HTTP is it will disguise all sorts of other faults in your system, right? When we had problems with the Racket web server, you say like, oh, probably the network. They're like, yeah, you're right, it's probably the network. It's like, actually my virtual machine crashed, but it's probably the network, right?
TCP, right?
Yeah, exactly. So no, I would argue that would be much nicer.
Got it.
Yeah. So I've tried to give you now more of a space here So we started with the static. We talked about property-based and property-free. I've talked about the dynamic, and again, we can talk about property-based. Natural question you can ask is, what is the property-free analog? And we can again do things that are loosely differential property-like, right? So you record, for example, a trace of a first program and run it against the second program and write a predicate over which of the things that are different that you actually care about versus which of the differences you don't care about, okay? So that's kind of to complete this picture, but what I want to point out is that this picture actually lies. When you're in the static world, there's a difference between whether you have the topology or not. There's a dual issue in the dynamic world, which is, do you have the state or not? In the static world, you can't really observe the network topology unless somebody gives it to you. In the dynamic world, it is similarly very difficult to observe the state of the controller. Now, you could get lucky sometimes. Maybe the controller is a Java program, and you use some Java API, like a debugging API, to get access to the state, and you can probe the state. But more likely than not, heck, if it's a C program, if it's one of Robert's programs, good luck, right? SOL. So there's this flip problem over here, and I want to put this up because I want you to really think about this picture, because there's very, very interesting questions that depend on topology and state, and both statically and dynamically, they are complicated to do because one thing is available in one case, the other thing's available. So we usually think of the static dynamic split as, oh, in the case of static, we can talk about all possible behaviors, but we can't talk about individual values. In the dynamic case, we can talk about individual values, so every counterexample is a true counterexample, but we can't see all the possible runs. That's the usual static dynamic split we talk about in the PL community. I want to point out where the network is concerned, there's another interesting static dynamic split that makes verification analysis questions much richer, much more interesting. And I also want you to think about this property-based versus property-free. Right? This column simply does not get enough attention at all. People love to live in this world because we have lots of great mathematics, lots of great tools. This world doesn't get enough attention. Part of what I want you to understand is the tools we have developed in this world, some of them, solvers, for example, are useful here too. Right? These eventually turn into search questions, and all this wonderful verification and AI tools we have for search over here are equally applicable over here. We just have to take the initiative to come and think about these questions and think about the form of questions we formulate. So that is the end of my talk. There's a few papers here if somebody wants to write down a reference or two, but really, screw that. It's just papers. So this is a slide I want to leave you with, and happy to take more questions.
Yes? The property I crave in these networks is always the shift from static to dynamic. So I want to know, I designed a network thinking it's static, and then suddenly spanning tree shows up and things being dynamic, then it shifts back after a while to static again. So do you also see the shift between the two? Because any network is a combination of both. Yeah, actually, so in some sense, when you're doing the analysis over here, you are assuming that essentially every time the network is in a static state, it's correct. When you're doing the analysis over here, you're assuming every time the network is in its dynamic state, it's correct, right? I don't know, and just really I don't know, of really interesting kind of phase changes that happen, because that would be fascinating. Because if you have a real phase change where it really does something interesting and goes through this quiescent phase and then goes to this new phase, then neither of these tools is going to be enough, and you really need something that's careful enough to sort of really shift between the two. Right? So in some sense, when we're in this reactive monitoring thing, we are thinking of it as like, look, we could take the properties we have, right? We have them as logical properties, not too hard to translate those into reactive programs in this sort of reactive sublanguage we have, and then turn those into monitors, and then even say this much of it we can discharge statically, this is the residual, right? I mean, that's an old PL trick. We know how to play that game, right? Partial evaluation, specialization. So we could do that. But what you're talking about is potentially much more fascinating. I just haven't seen that happen. And, one of these networking people probably will tell us where that happens. And then that would lead to an entirely new kind of verification question that we don't at all think about. Yeah.
Okay, so...
I think Wolf has a quick question before we finish. Yeah.
Is tierless the right answer in the sense that the control plane, it can be considered as a meta program? And as Phil was asking this morning, and as Gilad also pointed out with his mirrors, it's a wise thing to separate base level from meta level.
So I'm trying to understand. I want to make sure I understand your question. So you're saying
The
the
data plane and the control plane. I'm not an expert on SDNs.
sure, that's fine.
I thought like control plane is the one that changes the
That's right.
topology. So
Right.
it's like a program that actually defines the program.
That's right.
So it's a meta program.
Not to be rude, but did you miss the first few minutes of the talk?
Yes.
Okay, because that's exactly what I talked about, and I talked about why that's a terrible idea, right? Because so look, there's a really standard trade-off between giving ourselves more expressive power and giving ourselves an analytic power. Okay, so I don't actually know what the sort of verification status of things like the mirrors is. I'm going to guess not good. Okay, yeah, and so so if I wanted to live in a world where I really wanted to be writing generating programs, in fact, that was actually on the slide. It said this is a program generating. So you're absolutely right in your insight, your view over there. But if I wanted to live in that world, you're right. I don't want to use the current abstractions; they suck, right? And having some sort of abstraction, like a mirror-like abstraction, where I can really talk about these two different planes in an intelligent way, would be fantastic, right? I don't want to live in that world because I want to be able to do all of this stuff, right? And if our networks are going to be dependent on large chunks of software, I think it's really important that we be able to think about it. So the flow log, it's a multi-year experiment as far as I'm concerned to see how far we can push programmability and analyzability at the same time, recognizing that they're in conflict with each other, right? And in the 70s, people tried to do this, and basically they got mocked for trying this. But it's okay to try it again and get mocked once again, right? To see if we can build a language for both programming and analysis at the same time. So that to me is the real critical thing, is you can have all that power, and then you'll just make it even harder to know what your network's doing. Okay.
Okay, so to stay on schedule, we should really.
Thank you very much.